So a point estimate is a single number that represents your best estimate of something you're interested in. And it's your best guess for something that has a true value in the population. It could be, if we were talking about ages and we were interested in the average age of Hunter College students, for example. If you had to just give one number, either based off the top of your head or based on a sample that you took the average of, it would just be one number, like 38, and that is your best guess. But that does not give any indication of your uncertainty in that guess. That's where we get into providing intervals around those estimates. And instead of one number, a confidence interval has a lower and an upper value. Those values are typically going to be centered around your point estimate and go up and down by what is called your margin of error. So instead of just saying we think that the average age is 38, we might give a margin of error of 3 years. So plus or minus 3 years, so between 35 and 41, instead of just that point estimate. So the idea is to formalize the amount of uncertainty that we have around some population parameter like average age. Here's an example. Let's take a random sample of 309 infants. From that sample, we calculate their average birth weight, 119.6 ounces, and a standard deviation of 18.2 ounces. That might either be known from the population, that's going to be one scenario, or estimated from the sample is a slightly different scenario. And we took this sample because we want to estimate the average birth weight of infants in the population. Can someone give me an example of how this might fit into a public health study? Why would you be trying to estimate the average birth weight of some population? Yes?
You might want to compare whether the average birth weight of babies born to mothers is lower than the average birth weight of babies born to mothers who don't smoke.
So a good example, you might want to say whether there is a difference in the average birth weight compared to between mothers who smoked and mothers who did not smoke. That would be an example of a two-sample hypothesis test if you had observations of mothers who smoked and who did not smoke. In this case, we have only one sample, so we would have to compare to some previously established known value, something that there is no uncertainty in. So if we had a birth weight registry from which we could calculate the average birth weight of all infants born over the same period of time, that would give us an exact calculation of average birth weight in the population. And then you could do this with just one sample. You could calculate your average birth weight of, say, infants born to mothers who smoke, or anything else of infants born to mothers who are under 20, or anything else, and compare that to this reference value. And then, of course, when you draw samples, we know because of the sampling distribution, there's always some randomness in that average. The randomness is going to be smaller here because we have a sample size of 309. It's pretty big, so the variability in the average birth weight of 309 infants isn't going to be very big compared to the variability of individuals. But still there is some variability. And the question that we're going to be able to answer today is, what is the 95% confidence interval on the average birth weight of this population of infants? So we've got the point estimate, 119.6. We've got a standard deviation of, that's the variability of individuals. We're going to use those pieces of information to provide a confidence interval around the average birth weight in this population based on just one sample. Does that make sense? And that is distinct from this not scenario here. What interval contains the birth weight of 95% of all the infants in the population? Does that seem, that should seem like of course not, like I would never mix that up. You probably will mix it up at some point, and that's okay, but the more you can start distinguishing between those things, the better. It's a, you know, distinguishing between individuals and samples is what that distinction is. The interval containing the birth weight of 95% of infants, that would be found from the population distribution, whereas we're looking for a confidence interval on the average birth weight. You see average, you think sampling distribution. And you'll get tricky questions about this on the test, making sure you understand whether you're thinking about the sampling distribution or the population distribution. Repeat about.
You said this, you were saying that something would be found if we were population distribution.
Right, so the interval that contains the birth weight of 95% of all infants in the population, to answer that, you need the population distribution. You would need the mean and the standard deviation, and you could use the z-table, or you could use the empirical rule. You could go plus or minus 2 standard deviations from the population mean to get that interval. But in order to calculate a confidence interval on the average birth weight, that is going to be based on the sampling distribution and the standard error, not the population distribution and the standard deviation. Of course, the means are going to be the same, but the standard error is different from the standard deviation. And the standard error is, what is it compared to the population standard deviation? Yes? Yep, standard deviation over the square root of the sample size. So the standard error is always less than the standard deviation, which makes sense because the average properties of a group of individuals is less variable than the individuals themselves. So how do we construct the confidence interval? We're going to start from a sample. That is the data that we collect. When we go into a study and we observe 309 infants, that's a sample. We're going to calculate the mean of the sample data, and that will be our point estimate for the mean in the population. It's the best estimate that we have. Even though we know there's some sampling variability, the best estimate we have is what we calculate from the sample. And then we're going to calculate this margin of error, the uncertainty above and below that sample estimate, using the central limit theorem and the standard error. If we have a large sample size, all you have to do is add and subtract 1.96 times the standard error in order to get a in order to get a 95% confidence interval. So you calculate that standard error as sigma over square root of n, you calculate your sample mean, you add 1.96 times your standard error to get your upper limit, and subtract 1.96 times your standard error to get your lower limit. And you can use this, the normal distribution or the 1.96, either if sigma is known, so it's not estimated, or, and I'm actually going to change this A part here now that I look at it. This is not quite right. This is your advantage you get for listening to the lecture. This is really only if you have a very large sample, not just n greater than 30. I'm going to say 300. And just put in, call this very. So that the n greater than 30 was good enough for us to assume a normally distributed sampling distribution. But it turns out that actually that if we're estimating S, you underestimate the variability of that distribution a little bit, and that's what we're going to get into in the latter half of class with the t distribution. If you have a very large sample like 300, then it really doesn't matter. Normal distribution is fine. But if you estimate S from a small sample, or at least even not a very large sample, you're going to use the t distribution instead. The t distribution, if you're estimating S, is always safe. I'll show you the table a little bit later. Just it becomes indistinguishable from the normal distribution once you get to very large sample sizes. So here's a couple formulas for you just for calculating the 95% confidence interval, the 99% confidence interval, and in general for other confidence intervals besides 95 or 99. And this is under the normal approximation. And so these all involve calculating the standard error, and the way you calculate the standard error is a little bit different depending on whether you have a continuous variable or the proportion of a binary variable. But other than that, your calculation is the same. And I'm going to change this again to 300. A little hard to. I have a slide in here a little bit that'll show you how much of a difference it makes for n equals 30. It's not a huge difference, but it is a difference.